So our next talk comes from Arteris IP and Stefano Lorenzini, who serves as a functional safety manager over at Arteris. Stefano has over 25 years of SoC design experience, with 15 of them in functional safety. And throughout his career, he's actually been shaping the design or the landscape of functional safety at some of the most prominent silicon companies such as Intel and Cadence. I know Cadence is an IP company, but still. So today, Stefano will be actually detailing how Arteris and its impressive NOC technology approaches AI, machine learning, and functional safety, and kind of what Arteris's vision is for those three markets. Stefano, whenever you're ready, you can throw up your screen. And I'm sorry if I butchered your name too.
So let's jump in the first one. And the first slides show an architecture of a complex system on chip based on a network on chip. It is evident like the NOC play a central role in managing all the relevant data among agents and can be considered a sort of a data highway of the chip. It connects many different types of heterogeneous IP, like cluster of processor, machine learning array, memory, and many types of peripherals. A NOC shall support different types of interconnects to accommodate application-specific requirement. For example, coherent and non-coherent interconnects or subsystem interconnects, as well as interchip links to put in communication sometimes different dies. Also, other features may be important, like memory scheduler, for example, to optimize the accesses sequence to the external memory, as well as on-chip cache to reduce the number of accesses still to the external memory. So ultimately, a key prerequisite, in our opinion, for a NOC is the flexibility, with the purpose to accommodate different type of IP, protocol, and network topologies. This is just a snapshot of the Arteris IP customer portfolio divided by application domains. It counts about 200 customers covering all the more relevant marketing domains. Here in these slides, automotive ADAS application fit in the transportation section, while a generic AI application in the AI machine learning section. Arteris takes benefit from the experience of these two domains, let's say, to address AI applications specifically for automotive, like Inference, for example, for image processing. This background actually combined also with the functional safety know-how that Arteris has to assure adherence to the ISO 26262 standard. Arteris, in fact, has been a contributor to the ISO 26262 second edition in the past, and contributor also to the ISO 26262 part 11, that is the part that specifically address the guidelines for semiconductors. But let's now move the focus on the main characteristics of an AI SoC for automotive, and also highlight how they differ from general purpose AI chip. In these slides, as an example, we are comparing the Biden-Coulomb chip for data center application and the Mobileye Q5 chip for automotive vision processing. It is evident how the different workloads running on this chip set different requirements that ultimately lead to different architecture. In the case of the data center application, workloads are typically quite diversified, while in the case of an automotive chip, the workload is very specific to the application. Additionally, latency for sure play a different role in the two cases, being it much more critical for automotive chip because they are supposed to run or sustain a real-time application. In fact, the following slide just give a better idea about those architectural differences. Here on the left side, it is reported the architecture of a generic and non-automotive AI chip or general purpose, while on the right side, the architecture of an automotive AI chip. Non-automotive chip show, of course, a very high regularity, and they are built around homogeneous elementary processor that lead to a regular network topology. On the other side, automotive chips show quite a less regularity due to the heterogeneous set of elements that are the IPs to be connected, leading to a customized network topology, typically, as already said, application dependent. But for sure, the architecture in our vision is not the only difference. There are other important aspects that to keep in mind or in consideration that are described, in fact, in the next slides. So the remaining part of the presentation now will focus more on those aspects that will be the power, performance, area, safety, and also the schedule. Actually, still in our vision, automotive AI chip require to address these aspects even in a more efficient and optimal way if compared to non-automotive AI chip. This is due to the real-time requirement to be achieved at a reasonable or minimal power consumption and silicon area cost. But let's now step in the power aspect. Containing the power consumption is for sure fundamental, but it is not always easy. There are at least two main reasons why power consumption doesn't scale as we would wish. One reason is the silicon technology scaling, where wires can't follow the same scaling law as transistors do, for example. The other reason is the intensive off-chip number of accesses done to access the data memory outside the chip. And this is typically really relevant. Mitigation of this effect can be achieved adopting for sure sub-deep micron silicon technology like current 7 nanometer node, for example, but also it's required to adopt suitable architectural design choice. Like, for example, an aggressive power and clock gating techniques, or for example, increase the quantity of memory on the chip itself. Arteris has experimented the power saving up to 50%, in some real customer application, just adopting this kind of solution. In fact, the following slide show, let's say, some more detail about this. In this example, an SoC power management unit shown on the left side control directly an agent represented in this example by an AI subsystem, and connect also the NOC logic thanks to a NOC power controller feature. To execute the power shutdown and reduce the consumption, here the SoC PMU send a command to the agent and to the NOC, of course, respectively shutting down the AI subsystem first, and the portion of the NOC connect to the subsystem. Of course, the remaining part of the NOC still remain alive, obviously, to sustain the communication required by the other agents. This feature that is important for sure for power saving can be also exploited to implement functional safety features, like, for example, agent isolation to run BIST during the functionality of the chip, or a permanent isolation of a faulty agent from the NOC that is in some sense virtually disconnected to provide support for interesting feature like fail operational system, for example. Next aspect was the performance. The performance required to sustain a safety critical real-time application is typically achieved increasing the bandwidth and decreasing the latencies offered by the NOC. These requirements can be satisfied augmenting, for example, the quantity of on-chip SRAM, typically cache, in order to keep as local as possible the communication. And as a consequence, reducing external accesses to the memory. It's worth to note that sometimes to contain the latency, it's important to get a benefit from a specific NOC feature, like the multicast. That is a feature that allows to synchronously update coefficient typically used in Mac, okay, in order to implement the convolutional algorithm almost at the same time. So a sort of equalization or balancing of these updates of coefficients. This is very important in our experience, at least, to reduce the latency. In the next slides, in fact, we give more detail of the candidate, let's say, architecture to better satisfy, at least in our vision, real-time requirement. These slides report two different architecture. Again, the non-automotive on the left and an automotive architecture on the right side. The architecture of a generic AI chip clearly show an higher regularity, for sure. But at the same time, also a higher latency is paid due to the hops typically required to move from one switch to another. While the architecture on the right side, the one designed for automotive, show for sure less regularity, but also an optimal path architecture to connect master and slave agents together, minimizing also the number of switches to be traversed, hence the latency. In this case, software tools to configure the NOC architecture are really helping because they can select the best topology for the better performance. It's like to say that the user can provide to the tool the requirement he wishes to meet, and the tool automatically select the best architecture of the NOC or the best topology for him. Area is for sure another factor to keep under control because it impacts the yield and as a consequence the cost of the chip. Area can increase due to wires, for example, relatively speaking, because the wires don't scale with the technology as we wish. And also because of the increasing complexity of the chip functionality itself, because of course AI or machine learning algorithms are quite complicated. In this case, virtual channel, for example, can contain the number of wires, offering a single, let's say, or less physical means to transport multiple logical channel. While source asynchronous communication that is another technique showed here on the right side of the slides, can avoid implementing a clock distribution across longer distances, or can avoid sometimes implementing tricky resynchronization FIFO-based mechanism between different domains. Okay, but let's now focus on safety. That is one of the discriminating features for automotive AI chips. As already seen, a specific feature may be required for this kind of chip, like the isolation. We saw that in one of the first slides. But more in general, safety mechanisms are required into a network on chip as for any other IPs in the chip to guarantee the required level of ASIL. For example, ECC cover for sure an important role due to the high number of memory in the chip. we know that memory, in fact, are highly susceptible to transient. While, for example, adding a better redundant channel could create a backup path in case of fault between two specific agents, one specific initiator, for example, and a specific target. But not only specific safety features are required to design this chip, but also specific development step. Also, the process is important. So specific step must be in place to support generically the functional safety designing or flow, like, for example, the safety analysis that are really centric for this kind of implementation, and safety verification. It's worth to mention the importance of the fault injection, for example, as one of the most relevant verification means to provide evidences for the FMEDA. And according to our experience, a brute force fault injection approach doesn't work, at least for this complex chip, while a smarter approach is required to make the fault injection feasible. In fact, in the next slides, we report some guidelines in this sense. For example, in our opinion, I will say that the smarter way to address fault injection for sure is to use the safety analysis to drive what to inject or not to inject, and also how much to inject. But not only. For example, starting the safety verification process in RTL, in our opinion, helps because simulation obviously are quite faster, and they can also support an easier pipe cleaning and debug, anticipating problem capturing. For example, low detection, that could be one of the symptoms. In case of bad safety mechanism selection or bad safety mechanism implementation, as well as low workload controllability, for example, that is typically due to poor workload definition. So ultimately, only at the end of this process, we think that validating the result using the netlist become worth. Of course, still continuing driving the fault injection plan using the FMEDA. Finally, not for in terms of importance, of course, it's the schedule. Here, Arteris made recommendation, according still to our experience from the fields, is to involve a safety expert since the beginning of the design. In particular, to double check the AI contents, for example, that for an IP provider represent a sort of declaration describing what the customer will receive in terms of deliverable, and very important to double check the assumption of use reported into the safety manual, because our IP are developed as a safety element out of context. Typically, this is what avoid the lifetime change order that may delay the project, if not even make it tricky to resolve. So as a conclusion, let's say there are three major aspects in our vision to keep in mind when designing an automotive chip with AI capability. First, the increasing demand of high bandwidth and low latency lead to spend more and more effort in matching this requirement. So first conclusion is that a flexible and configurable NOC topology is the best way, if not probably the only one, to meet this competing requirement. Second, the power consumption budget get less. So aggressive clock and power gating techniques are fundamental. And third and final, functional safety features are really key. So the network or chip, as any other IP, require its own safety mechanism, and possibly also specific feature to enable fail operational system. Thank you.
That was a fantastic presentation. You did a really good job. So we got some questions already streaming in from the audience. So I'm just going to start off with that, if you don't mind.
Sure.
So the first one we got is, how does Arteris and their NOCs kind of deal with error detection? And do you guys have any correction schemes, especially for the ADAS applications?
Yes, of course. Let's say it's the architecture, the safety architecture is strongly oriented to ECC, safety mechanism. And we have both. We have the possibility to detect error and also correct. Of course, correction in our case can occur in case, let's say, when only one fault occur, and detection when two fault occur. So yes, we have also correction that allow you to implement a sort of a fault tolerance system.
Do you mind also kind of minimizing your screen or stop screen sharing so that we can kind of see you on the full screen?
I'm sorry.
There you go.
Sorry.
Perfect.
Yeah,
Thank
sorry.
you. No worries.
I didn't realize that at all.
Okay. So then the next question I kind of have is, you speak a little bit about your tuned architecture, but can you kind of walk us through how your software selects what is the best switch for the job?
Right. That's a good point, because we rely a lot on our software. Let's say that the software, from a concept point of view, what he wants to solve is to offload the customer, the user, from defining the architecture of the NOC. Okay, but allow you to start from requirements. I want, for example, to reach this kind of latency, this kind of performance between this specific agent and this other, this level of quality of service, and so on. And the tool automatically for you propose the architecture. Okay, so you just set the constraint at requirements level, and the tool does the design job for you. So it's a sort of, in bracket, a high level synthesis that export the RTL code. In fact, the RTL code is one of the most important deliverable, of course, because for obvious reason, but we provide also other interesting deliverable together that allow you to do more in general exploration for your performance. For example, system sim model, or let's say some specific verification environment where you can test alone your NOC if it is matching your requirement. And since we are talking about safety, we export also automatically an FMEDA that is, how to say, scaled up or down, scaled according to the specific configuration of the IP. In fact, probably I didn't stress one of our most challenge, that is, let's say, offering a solution that is really highly configurable. We have really tons of parameters that the user can set, and the RTL, of course, change accordingly. And if you reflect this in the safety space, of course, also the FMEDA should reflect the same things. Okay, so we export also automatically, for example, the FMEDA. So essentially, we give all the main means to check and explore if the NOC, in terms of performance, functional performance, let's say, and safety performance, is in line with the expectation.
Okay. And then kind of also continuing down that vein, when you guys, when the NOC is generated, do you guys also generate, or the NOC and topology is generated, do you guys also generate patterns for that injection testing for your RTL? And like, yeah.
Right. Yeah. Okay, that's a good point. We generate functional patterns, so no fault injection pattern. I think you have in mind the question wants to ask if we provide also the workload to do fault injection in house. This is the meaning of the question, probably.
Yeah, yes, that is. Yeah.
Yeah. I got it. Now, let's say we don't offer yet this, but I can tell you that we are working on this. because it's fundamental, because what we do typically is to assess or sometimes certify our IP using fault injection in-house during the development. But we consider some specific configuration that we consider, how to say, not realistic, that makes sense, let's say, generically speaking. Representative, this is the word that I was missing. But after that, of course, the tool is not replicating the fault injection. It is just modifying the FMEDA for you, because this is the starting point. And then the customer has the option either to rely on this FMEDA or to implement the fault injection in-house. So what we want to offer on top is an additional mechanism that make it easier, let's say, setting up this stuff at the customer side, because you know, it's not a peanuts. It's a very costly process. Yeah.
I agree. So this is a little bit diverging from your talk, but kind of looking forward.
Sure.
Is Arteris looking into kind of interconnect technology and solutions for chiplets? And like, how is that going to start to play into your like the functional safety of it all and the AI ML?
You mean to connect different chips together?
Exactly.
Yeah,
like
yeah. There is probably just one arrow in the first slide that show that we have this possibility, just a small detail that of course you couldn't capture. But yes, we already have the possibility in the current product to create a special socket, let's say, to connect an external die, typically if we are talking to multiple die on the same chip, or even different die in different chips, of course. So this capability is still there.
Mm-hmm. So I kind of want to also discuss when you talk a little bit about area. So we know that some of the common interconnect technology and interfaces are quite clunky. Does Arteris have any custom solutions for interconnect technologies that help reduce area? Do they have like custom PHYs? How does Arteris kind of approach the area aspect of interconnects?
Okay.
Oh, you muted yourself accidentally.
Okay, can you hear me now?
Yes, you're good to go.
I didn't touch nothing. I don't know what I did. It's realistic. This is my hands as well. Okay.
It's the ghost of Zoom present.
Yeah, maybe. Yeah. Okay. So the question is if we offer some custom things to address the area issues, right? Is this the question? But for custom, you mean RTL at RTL level, or sort of hard macro? What do you mean?
At the RTL level.
No, at the moment we don't have, at least look into the portfolio, we don't have any custom pre-packaged solution, let's say, because what we have experimented is that every chip is different. I don't know if this could be, let's say, possible. In any case, no, we leave completely freedom to the user using the tool to generate what they want. But of course, we provide a strong support through our field application in order to teach them first and drive them through this process in order to minimize the area. So essentially, I could answer that our field application engineer helps in reaching this area minimization, but no, we don't offer any custom prepackaged solution at the moment.
Okay. That's pretty cool that your like FAEs kind of come in and they like do a custom solution for each of their customers.
We strongly relied on the field application engineer. Yeah.
Okay. Well, I think that's actually all the time we have for Q&A. And I just want to say thank you very much for coming. I know you're a very, very busy man. You've welcome. And I thank you for taking time explaining us kind of like Arteris's vision on automotive AI and functional safety.
It was really a pleasure.
No, and you did a great job. Like I learned so much about like what you guys do for functional safety. So thank you so much.
Thanks a lot. Have a nice day.